Alright, section 4.5 is on page 180, talks about the superposition principle and undetermined coefficient revised. So kind of a combination of the homogeneous and non-homogeneous, but now we're adding to it. Suppose you have g of t, which is the forcing factor, and that consists of multiple, not one type of functions, but multiple type of functions. So suppose that y sub 1 is a particular solution of g of t, and suppose that y sub 2 is another solution of g of t. Then any linear combination of those two would be a solution of the differential equation, which is this. So I'm going to start off by saying what can we do and what we can do. On 9 through 16, decide whether the method of undetermined coefficients. If you remember the undetermined coefficients, I'm going to go back really quick. Undetermined coefficients specified three types of problems. Specified a forcing function of an exponential, sine or cosine, and a polynomial. So keeping that in mind, again, together with the superposition, all what the superposition says, if you could find one solution to this and another solution to this independently, then you could say that the combination is a solution. So here we're saying, well, let's see, can we apply this superposition idea on the following problems? And what really dictates is two things. One, linear differential equation with constant coefficients, that checks. This is e to the 2t plus t e to the t plus t squared. So yes, I know how to do an exponential, another exponential, and a polynomial I know how to do definitely. So we don't need to solve, we just need to say yes, can decide whether the method works or not. When I look at this problem, I notice this is linear, but non-constant coefficients. So because of the non-constant coefficients, we cannot use the method of undetermined coefficients. Basically, nothing in this chapter so far. Looking at number 14, at first glance, well, you say, hey, look at that. That's a linear and constant coefficients. Right? So this checks. 2t plus 3 is a polynomial, that's very good. Sine squared, we have a problem. But if I think of sine squared as 1 minus the cosine of 2t divided by 2, then yes, I can. Because cosine of 2t I could figure out. Cosine cubed I can do. When I look at number 16, linear, that's a must, and constant coefficients. Which means yes, that checks. T squared e to the t sine of t I could do. 8t cosine of 3t I could do. How about an exponential? Can't I say 10 to the t is actually e to the natural log of 10 to the t? And that is e to the t times natural log of 10. So that's a form of an exponential. So yes, I can. Now what? Well, let's apply that. Let's apply this idea and show you how this works. On the first problem, it's kind of like what we did before. That's not a problem. Actually, they really don't get that much involved. They just say list them. So here, I'm going to add to this. This is extra practice for what's to come. I'm going to list the form of the particular solution. I'm going to say on number 10, the particular solution will be a e to the 2t. This right here is linear. bt plus c, that's linear, times e to the t. And I have a function by itself that is quadratic. I used a, b, c, d, t squared, et plus f. Of course, the fun part is finding a, b, c, d, e, and f. Now, the beauty of this, I could take this by itself and find a by plugging that in. I could take this by itself and find b, and I could take this by itself and find c. So I could look at this equaling just this piece, find a. This linear equation, this differential equation equaling only that, find b and c, and this linear differential equation equaling t squared, and use the green and find d and f and add the results. That's what this is saying. This says if you could find one of them by itself, the other by itself, sum the result, you're set. In 12 I can do. In 14, if I look at this, this is really 2t plus 3 plus a number. So the particular solution, one of them is going to be at plus b, plus the cosine is going to be c the cosine of 2t plus d the sine of 2t. Similarly, I could take this differential equation and set that equal to this alone and solve for a and b right there. Or actually, I should say right there. And I could take this differential equation again and set it equal to the cosine of 2t negative and find c and d. And that's really how it works. So on problems number 18, they say find the general solution. Well, here, it's really obvious what the particular solution is, but we learned that we need to find the homogeneous solution first. This is a second order linear differential equation. Let y equal e to the rt, y prime equal r e to the rt, y double prime equal r squared e to the rt. I have e to the rt multiplied by r squared minus 1 equals 0. So e to the rt can never equal 0. It must be that lovely. It must be that r equals plus or minus 1, which means e to the t, e to the negative t is a solution. So the general solution so far is the complementary plus the particular. I got half of the problem, c1 e to the t plus c2 e to the negative t. I still need to figure out the particular, and that's where this comes in. We say the particular is a general of a linear equation, at plus b. I need two derivatives. Y prime is a, y double prime is 0. So 0 minus at plus b must equal the negative 11t plus 1. Negative at minus b equal negative 11t plus 1. So that means that I got excited, didn't I? So the number in front of t must equal the number in front of t, and the constant must equal the constant. That indicates that a must be 11 and b must be a negative 1. So that means this is 11 and that is a negative 1. Well, plus 11t minus 1. That would be the general solution. That's the least amount of work you could do. So the catch, every time they say find the general solution and you are dealing with the particular component, you have to find it. Unless they say list the particular, do not find it. I look at problem number 20, another example. Well, I'm going to let y equal e to the rt. I'm going to get y prime equal r e to the rt, y double prime equal r squared e to the rt. So I'm looking at e to the rt multiplied by r squared plus 4 equaling 0. So e to the rt can never equal 0. R equal plus or minus 2i, which means cosine of 2t and the sine of 2t would be the solutions. So y is going to equal the complementary plus the particular, y is going to equal c sub 1 the cosine of 2t plus c sub 2 the sine of 2t. That part is done. I'm going to go on the side and figure out what the particular is. The particular solution in this case happened to be a the sine of theta plus b the sine of theta. Luckily those are the same, otherwise I would have had to do two of those. I need two derivatives. Y prime is a the cosine of theta. Okay, you guys know what I mean, right? This is so embarrassing. So this is negative a the sine of theta plus b the cosine of theta, and y double prime will be negative a the cosine of theta minus b the sine of theta. And if I take y double prime, which is negative a cosine of theta minus b sine of theta, plus 4 times, so 4a cosine of theta plus 4b sine of theta, and that's going to equal those two, sine of theta minus the cosine of theta. So here I'm looking at 3a cosine of theta plus 3b sine of theta, and that equals sine of theta minus cosine of theta. So 3a must equal a negative 1. That makes a negative 1/3. And 3b must equal a 1. That makes b positive 1/3. So the solution would be minus 1/3 cosine of theta plus 1/3 the sine of theta. And that would be my answer. The only way I could find those coefficients, if you give me C1, if you give me the initial conditions, which is the next problem. Okay, 24 is next. And this says y double prime equal 6t. So here, I really don't need, I could solve this straight. I could say this is separable equation, right? I could integrate once with respect to t and say y equal 3t squared plus c, or c sub 1, and integrate again with respect to t and say y equal t cubed plus c1t plus d, right? That's a way of doing this. I could use initial conditions and say y of 0 is d, and that is a 3. I got this to be 3. Y prime is 3t squared plus c1, and y prime of 0 would be 3 plus c1, and that equals a negative 1. So c1 is negative 4, and I could say out of this y equals what was it? Y equal t cubed plus c sub 1 t minus 4t plus 3. And if you're not liking this, that's okay. You could say let y equal e to the rt, y prime is r e to the rt, y double prime is r squared e to the rt, and that means right there that r squared e to the rt equals 0. Well, e to the rt cannot equal 0. It must be that r squared equals 0. So e to the 0 is 1, and e to the 0 is 1 times t. Y would be c1 plus c2t. The particular solution is at plus b. Take two derivatives. Oh, at plus b, but do you see that that's included right there? I need to modify. So can you see how, if you really don't look at that, you're going to really have to make a lot of adjustments. So you're going to modify, multiply this by t. that's still at squared plus bt. This is already right there. You're going to modify again. How many times do you modify? As many times as it takes until none of these solutions here are in there. So modify once, modify twice, and I need two derivatives. That's 3at squared plus 2bt. Y double prime is 6at plus 2b, and it says the second derivative 6at plus 2b equal 6t. That means 6a equals 6, a equal 1. And two b must equal 0. So this is a 1 and that's a 0. Doesn't that mean that the particular solution is simply t? No, I'm sorry. It's right there. I forgot. We modified. So this is the particular. So if I put 1 there, doesn't that make this t cubed? And what do you notice? There's no need to do all of that. It's right there. And if you follow the steps, you get the same thing. So, you know, if you see a problem, it doesn't specify how to do it. You can do it any way you want, you know. If it says use the specific method, then you could. And how about number 28? Same deal. Again, the beauty of this, I could do those individually. I'll show you what that means. If I look at this part, so y is going to equal the complementary plus the particular. Let's get the complementary out of the way. I'm going to let y equal e to the rt. Basically, I'm setting this equal to 0. Y prime is r e to the rt. Y double prime is r squared e to the rt. E to the rt multiplied by r squared plus r minus 12 equal to 0. E to the rt cannot equal 0. It must be that r plus 4 into r minus 3 equals 0. R equal negative 4 or 3. E to the negative 4t, e to the 3t. Luckily, that's not any of those. So far this is what I have. So far I have y equaling c sub 1 e to the negative 4t plus c sub 2 e to the 3t plus the particular solution. Let's get the particular solution. The particular solution consists of 3 components. I could do them all one shot. I could do a e to the t plus b e to the 2t plus c for the constant. Or I could say, you know what, forget that. I'm going to do them one at a piece. I'm going to say y1 for the particular is going to equal a e to the t. I'm just taking this piece. Y prime is a e to the t. Y double prime is a e to the t. So if you take y prime a e to the t plus a e to the t minus 12 a e to the t, that should equal e to the t. You could do that. That's the whole theory of superposition. Negative 10e equal e to the t. That indicates negative 10a equal 1. So a is negative 1 over 10. Negative 1 over 10. So far, I have one of those. Minus 1 over 10 e to the t. Then I'm going to go for the second piece of the superposition. Okay, let's not do that. Okay. I'm going to go for the second piece, this piece. So I'm going to take this equaling this. In that case, what would change? I will say y particular is going to be a e to the 2t. Y prime is 2a e to the 2t. Y double prime is 4a e to the 2t. And now if I plug those in, I'll say, look at that. That right there is, I'm going to write it down here. It's going to be 4a e to the 2t plus y prime plus 2a e to, you could use the letter b if you like, and minus 12 times, and that's going to equal only that component. That's going to be 6 of those. Negative 8a e to the 2t equal e to the 2t. Negative 8a equal 1. A is negative 1/8. So in this case, negative 1/8 minus 1/8 e to the 2t. And the constant is really easy to play with. You're going to let y equal b, y prime is 0, and y double prime is 0. And here you're taking negative 1 equaling this. That will make it 0 plus 0 minus 12b equal negative 1. b is 1 over 12. That would be the general solution. Now what's missing is y of 0. y of 0 is c1 plus c2 minus 1/10 minus 1/8 plus 1 over 12, and that equal a 0. So that means this is not as simple as it looks. I'm guessing the LCD is, oh my god, this is a big mess. C1 plus C2 equal, and let's see what those are. I'm looking at 1 over 10 plus 1 over 8 minus 1 over 12. I'll come to that in a minute. And if I take a derivative, of this down here, y prime will be negative 4c1 e to the negative 4t plus 3c sub 2 e to the 3t minus 1/10 e to the t minus 1/4 e to the 2t. And if I throw a 0 in there, I will get a negative 4c1 plus 3c2 minus 1/10 minus 1/4, and that equals a 3. That means negative 4c1 plus 3c sub 2 equals 1 over 10 plus 1 over 4 plus 3. This is what I need to solve to find c1 and c2 and plug those, and that's that. And I'm going to cheat a bit and find what c1 is and what c2 is. I'm going to use, where is it? My calculator. And I'm going to go for systems of equations. I have two systems. Enter. Tell me the coefficients. 1 for C1. 1, that's the purple. And I'm going to input all of this mess as I see it. That's not a problem. The calculator could do that. 1 divided by 10 plus 1 divided by 4 plus 1 divided by 8 minus 1 divided by 12. And if I tell it to solve, it will tell me that solve. It's not solving. Why is it not solving? Oh, it tells me, let me just double check really quick. Did it register? Second, I have two equations. Oh, a sub 1, a sub, okay, I get it. It listed that way. I don't know that well. Okay, so we said 1, enter, 1, enter, so it gave me the solution. And I'm taking, what did we say? We said 1 divided by 10 plus 1 divided by 8 minus 1 divided by 12. And if I ask it to solve, some reason it's not. Oh, the second equation. I only give it one equation, forgive me. The second equation has a negative 4, so negative 4, enter. Is that a 3? That's a 3, enter. And a 1 divided by 10, I was only inputting one equation and I was asking it to solve, and how is it going to solve? Plus 3. Now you ask it to solve. And it tells you what C1 and C2 are, so again, I'm going to cheat and say this is negative 0.42. And this is negative 0.5596. Now, of course, I could find a common denominator here. I could say that is 4 times 3 times 5. 4 times 3, no, 8 times 3 times 5. There it is. That's the LCD there. And here the LCD would be 40, actually 20. And you could clear that out and come up with the equation. I'm just trying to save time because I'm already at 25 minutes. And normally I don't do 28. I just wanted to do it. So you could put in a negative 0.42 right there. And you could put in a 0.5596 right there. And there's the full solution. And you could see this is a lot of work. That's really, we don't solve them. I mean, you could do that in a calculator a lot easier. The idea here is for you to really grasp the concept. Here they say, determine the form of the particular solution. Do not evaluate. Just the form of the particular. Again, particular is a lot of work. So, same deal. Y is going to equal the particular plus the complementary. Okay, I can put them in that order. Let me find the complementary first. The complementary, you set that equal to 0. You let y equal e to the rt. Y prime is r e to the rt. Y double prime is r squared e to the rt. And that will be e to the rt multiplied by r squared minus 1 equaling 0. And that would make it e to the rt cannot equal 0. So r equal plus or minus 1. The reason you need to find this first to know if you need to modify this or not. So the complementary solution, so far this is what I have. C sub 1 e to the t plus C sub 2 e to the negative t. Now, I'm going to look at the particular. The particular solution, I notice all of these are e to the 2t. Wouldn't that be t squared plus t plus 1? So, the particular solution is going to be what? Since I don't need to modify, those don't match. A polynomial a t squared plus bt plus c. A polynomial of second order or quadratic times e to the 2t will do. And that would be it. Of course, as you see, the fun is finding all of those. And, okay, that wasn't intended. The homework is right there. And that concludes this section.